Hello and welcome. Here we are in lecture 16. So we're actually going to kind of start a new sequence of lectures starting today. So we've covered so many, language features the last few weeks, design techniques, etc., case studies. Now we're going to kind of take a step back and talk a little bit more about the physical aspects, right? We're just at a very high level, but the reason why we need to consider it is it's going to impact our design, and we should definitely be doing this, right? And so there's going to be a few sequences of lectures in a row starting today, Friday, as well as next Monday, where we're going to kind of dive a little bit into some of these more physical concerns, right? And, no worries if this is your first time seeing some of this stuff. We're covering it. So here we go. So in particular, we're going to talk about a couple things. We're going to talk about why, or what is physical design, and perhaps how you might go about optimizing for it. And then we're actually spending a lot of time talking about memory, right? And the reason why we're talking about memories is that they are one of the most impactful things you kind of can decide early on in your project design process that can really have a big impact, right? So we're talking about not just memories, but some of the concerns as well as ways to optimize them. So let's get to it. So let's kind of remind ourselves where things fit in here, right? We've been talking a lot about hardware design, and so far we've been writing Chisel, right? And it runs in a simulator, and yeah, we design hardware, but at this point it's just kind of the specification almost, right? I mean, Chisel is just a description of the cycle level behavior of your design, but it's not, implemented, right? It's not turned into something like an FPGA. It's not turned into a chip. So actually the process of, making that real is physical design, in particular for an ASIC, making an actual compute chip is that process, right? And so why should we be optimizing this? Well, usually it's to improve efficiency under some metrics, right? Now, it could be efficiency under, performance per unit cost, performance per unit power, or whatever it might be. And the question is, well, why are we doing all this, right? So if you're talking about designing custom hardware in some sense, you should already be thinking about, I have an application or scenario where I need a certain performance or efficiency target to be met, right? Where if someone asks me to solve a certain problem, normally the thing you would do is you go out and you write code. And perhaps you write code in a language like Python because it's easy and friendly. And perhaps if that's not fast enough, then maybe you can write that problem in C or Rust or something. And if that's not fast enough, then maybe we need to go specialized hardware. And of course, it's worth appreciating just in the modern era, here we are in 2022, how there are little processing cores everywhere, right? So software is really kind of eating the world right now. It's been doing this for decades, and it's just continuing, right? A couple of years ago, I remember being very surprised to find out that, like in a Thunderbolt cable, an actual like cable, you think just wires wrapped in rubber and plastic, there was 3 ARM cores, right, in a cable, right? So I mean, there's processing cores kind of lurking everywhere, and they're getting surprisingly capable, right? They aren't necessarily just your old school 8-bit or 16-bit microcontrollers. These can be 32 or 64-bit processors, even run Linux, or have like a vector code processor. They can be quite substantial. It was actually now 6-7 years ago when Apple first started putting out of order processors in their Apple Watches, right? So you have an out of order core on your wristwatch, right? So I mean, it gives you a sense of both how cheap and how prevalent and how common these cores are, right? So for a lot of applications, writing software to run on some embedded core somewhere is really a good answer, right? So the reason why you aren't doing that is you've identified for your application scenario that you need a certain performance or efficiency target, right? You have a reason why you're doing this, right? And perhaps you're targeting FPGA to get the results today, or maybe you're planning a future chip for the future, right? But the point is, the reason why you're going through this effort is you're trying to reach a certain performance or efficiency target, right? If current CPU can get the job done, trust me, not only is software code much easier to develop than developing your own custom chip, you also can buy those already, right? I mean, plenty of manufacturers are more than happy to sell you existing chips, and you can tap into the cost savings provided by the massive volume they have, right? Many customers can buy the same kind of embedded processor chip, and thus those chips can be really cheap, right? If you're gonna go out and build a custom chip, you need to really know why you're doing it, right? And so we're gonna kind of, I'm making this very clear right now, make sure you have that motivation. This is kind of an implicit background, but something you should be aware of, right? Is taken as a given that you have a performance efficiency target. That's the reason why you're doing all this, because otherwise, you should just go write software and buy an off-the-shelf tiny microcontroller, or maybe a embedded processor on a microcontroller. But so we're doing this because we care about efficiency, we care about performance. Running our application on a general purpose processor just isn't getting it done, right? And so When we're optimizing, of course, we want to be doing so in a very good way, right? We want to make sure it's most profitable. And so for a given optimization, rather than just leaping out and doing it, we should consider what else can we do, what might be the maximum or even reasonable benefit this might provide, and what might it cost to get there. And usually cost maybe some sort of engineering effort or some sort of complexity. You kind of need to understand, well, is that worth it, right? But at some point you ask yourself, okay, why am I doing this, right? What's the point? Okay, so what are we optimizing for? Well, you've heard me say this before, and I'll be a little more explicit again. I'm talking about PPA, or power, performance, and area, right? So all three of these really matter for a physical thing, right? We're talking about building specialized hardware. We're talking about, eventually it's being a real thing. So power, of course, is extremely important, right? This is the one of the most important, if not the most important metric in modern hardware design. We can definitely build chips much faster than we'd like to. Much faster than we can currently, and the limiting factor isn't so much other things, it's actually usually power, right? So this is usually kind of our biggest constraint, right? So how does this matter, right? Well, for mobile devices, which is the common case nowadays, it impacts battery life, right? The more power your chip consumes, the less time the same size battery will last, right? So if you can make your chip take less power, your battery life lasts longer. Or even better yet, perhaps if your chip takes less power, you can make the battery smaller, make your device thinner and lighter, and make somebody really happy, right? So consuming less power, of course, is great. That's going to help make a smaller mobile device or have a longer battery life. There's also a heat problem too, right? And this happens both in mobile and for plug-in-the-wall kind of things, right? Where for mobile devices, yes, this actually happens with some of these smartphones. There are concerns about, for that momentary time when a smartphone really is, going all out, maximizing its CPU and its GPU, you don't want the smartphone to get too hot to hold, right? And there's limits how much power it draws, which are put in simply just for thermal reasons, right? We don't want to make sure this thing gets too hot, etc., right? You burn a lot of power, you're going to create a lot of heat, and it needs to go somewhere. And then, of course, for desktops or laptops, I think we're all familiar with having a warm lap from a laptop, or having a really big or loud fan on your desktop for heat. So I mean, this is something we've all kind of experienced, right? And so reducing power can really kind of reduce these other complexities, right? And realize that in some cases there's like limits. Like I only have a smartphone runs with so much power, otherwise it burns my hand. Well, if I can reduce the power consumption, if I can improve the efficiency, that is, I get more done per unit power. Thus, I'm running at that max power level, I can get more done, right? So these are all things important. And then, of course, finally is cost, right? Of course, if your device burns less power, this is more important perhaps in a data center, your power bill's smaller, right? So I said power is first, it's the most important, but it's going to impact things, right? And then, of course, there's performance, right? Like I said, at some point, there is either efficiency or a performance goal for why we're doing this. And so performance matters, right? It's how fast I complete the task, right? And sometimes it's, it's doing a task once. Sometimes it's, a certain more exotic metric. Maybe it's like, I want to do something in real time, kind of continuously, and have a certain, rate of, okay, well, I'll have, real-time performance with, lag only 0.2% of the time or something, right? And so these kinds of metrics. But there's some sort of metric there for performance. And then finally, there's area, right? And area is important for both chips and for FPGAs, right? So on a custom chip, area is basically a proxy for cost, right? The smaller your chip is, the more chips it can make at the same time under manufacturing, and thus the price per chip is lower, right? Then we figure out to manufacture a chip, of course, and make these big wafers, and the cost to make a wafer is roughly constant to some extent. And so, yeah, the more chips you get per wafer, the cheaper they are, right? So if you can make your chip smaller, you can fit more chips per wafer, and you can save a lot of money or reduce your costs. And remember, cost isn't like the same thing as price, right? So you as a company are more than able to just increase your profit this way, right? And then, of course, FPGAs, right? When you're thinking about, deploying FPGA in an actual device, in an actual, application, however big your design is going to determine how big an FPGA you need, right? If you can make your design smaller, you can get away with buying a smaller, cheaper FPGA, and that'll, have various benefits, right? So these are all three important metrics. As I kind of mentioned the last time I brought up PPA, is that sometimes in software we're only worried about perhaps performance or perhaps maybe memory usage, but we definitely don't worry about power too often in software, and we usually don't worry about three metrics simultaneously. Like if you have an application that is compute bound, you're really worried about performance. Memory capacity usually isn't the problem, or if you have a problem that's really capacity bound, then usually performance is the problem. You'll find for hardware that you're commonly hammering on all three of these at the same time, right? You want to improve one, It's going to cause issues in the other two. You're going to need to have some sort of trade-off. We're going to talk about exploring those trade-offs next week, right? Yeah, so you usually have this kind of more complicated optimization goal of having 3 things to optimize for. And so when you're optimizing, of course, you need to have a goal. It's nice to say, oh, I want things to go fast. I want to be efficient. But what does that mean? And so there's kind of various things that happen to a design team when they're trying to figure out how to go about designing a project, perhaps based on some initial estimates as well as, some knowledge of the domain. You're going to figure out first what your implementation technology is, right? So when you're optimizing, usually you don't optimize your design in the abstract. Usually you optimize it for a specific scenario, right? I want to reach this performance goal under these constraints. And so one of those constraints is your implementation technology, right? So if I'm making a custom chip, which foundry, which technology node? Am I using a 14 nanometer or a 10 nanometer node? And, what implications does that have? Or, okay, I'm shooting for an FPGA, and let's say initially I'm shooting for this particular size of FPGA, right? And if I can make it smaller and shrink an FPGA, people will be happy with me, right? So, but you need to have that particular implementation technology going for, right? Because some optimizations won't be super portable. In software, if you go through the effort to make your algorithm faster, usually that's going to help a lot of platforms. In hardware, sometimes that will, sometimes that won't. There's different trade-offs for different ASIC processes versus different FPGA technologies. So they may not be as portable. Additionally, right, if you think about like software, like a lot of processors really look kind of the same. Yes, it's Intel this year versus AMD 5 years ago, 5 years in the future, but it's kind of similar. The hardware technologies under the hood are actually in some ways more different. They kind of do have some more significant changes between going FPGA versus ASIC. And so, yeah, when you're optimizing, you are kind of really optimizing with target in mind. Okay, and so then when you're optimizing, it's important to measure first. This is true for anytime you do performance optimization. Is know why you're doing this, right? So, okay, you have a goal. See where you are now. See how far you are from that goal. If someone tells you there isn't a goal, just go as fast as you can. That's not really a good situation to be in, right? Because you'll never know when you're done. You don't know if it's possible. It's better to have a goal and to target it, right? And if it turns out you reach your goal in not very much effort, then you reach your goal in not very much effort. Maybe you can overshoot it. But you should definitely have a goal and you should measure, right? You should know where you are, right? So one thing to say, I make my hardware design smaller, but you need to know how much it takes, how much area it takes now. You need a way of knowing which area it takes. So that way you know when you do optimization that you've actually made it better, right? So it's really good to kind of like set, know which technology you're using, have goals, start measuring things, and then you can start worrying about actually applying some optimizations. And you remember, as part of our Agile design process, I encouraged you to get things running first, right? And get things working, close that loop, and then worry about deferring some of those optimizations. Well, part of why you're deferring some of those optimizations is you need to figure out if you actually need them, right? When you actually see the target you're shooting for and the constraints, maybe you realize that this one that you're kind of afraid to do and you need to be a lot of effort actually is necessary. And sometimes for optimizations, you can kind of do some back-end envelope math to figure out, okay, if I did this and it worked as good as it could possibly imagine it can work, at most, it give me like, this many times improvement or something, and then you can kind of go from there. Now, and the good news is, when we're talking about how we're going to do this, we can use a hardware generator, right? So, before, if you had like tons of Verilog, those kind of static design, if you wanted to perform optimization, you had to change a lot of code. And now what if you want to, have, your old version versus the new version, you have to have like 2 copies of your code or something. It got really ugly, right? With a generator, you can go ahead and as you start applying optimizations, you can make these configurable, generated features, right? And so what's great is also, rather than having, let's say there's one component your team has and you keep revising existing Verilog, you end up with like 5 copies of Verilog or 5 projects for the same thing. When you get a new project, maybe it'll match one of the old uses, or maybe it won't, right? Versus with a generator, you have a better chance of being reusable, right? You can kind of have these optimizations and these features kind of be easily turned on or turned off. You can try them out. Perhaps, it's not just a single switch, but it's actually a parameter, right? You want to, see if you make this 2-way, 4-way, 8-way, some sort of, knob is actually changing topology in a certain parameterized way. Having generators is going to ease the exploration process, right? It's going to be easier for us to kind of try different things out. Sometimes it's hard to know which is going to be the best in advance. There's people who've made, entire careers, lots of research papers as well on how to, do best to do design prediction and modeling before you go out and building the hardware design. And the reason why is, it's so expensive and hard to do this. Well, with generators, you actually can try out multiple variants cheaply, right? Where there's making a generator and actually produce the variance. That's the effort. Actually having the tool run multiple times to, generate numbers for all the different variants, that can put a significant load on your, cluster for running the tools. However, I think that's money well spent, right? That's tools doing work, not humans doing work. And rather than trusting a model, you can say, oh, wait, here's what actually came out of the tools, right? So a generator is going to make this a lot easier. And as I said, on the last slide, right, we're making trade-offs across all three of these PPA metrics, right? And so if you're going to make these trade-offs, you need to understand quite concretely and quite quantitatively where you are and where you're going, right? Because, yes, this optimization, trades area for performance. I understand that, but knowing if you need to take it or not, it's going to be very much depend on the numbers. Okay, am I, above or below my area goal? Am I above or below my performance goal? Which one do I need to, trade? And so you really need the numbers for that. And so, yes, when we start optimizing, you have an technology, selected. You need to start measuring it. And then generators can help us kind of explore this process. Cool. Okay, I'm going to pause here for any questions so far. Okay, well, let's keep going. So, many of you may be very familiar with kind of doing software development. Perhaps you've gone a peek inside of a large industrial project as an intern or something. And today I'm going to kind of, have a, exaggerated, poignant contrast, which, is a little bit, hyperbolic, but let's go with it, right? So think of the easy world of software development versus the hard world of hardware design. And like I said, once again, these are caricatures. So in software, ideally, when you have a lot of developers working on a project, much of that effort is going to go into the implementation, right? And so, yeah, you're going to write a lot of features, you're going to test those features, but that's it. When it comes to optimizing it, let's say someone says, you know what, Slack is really slow, right? You have to go not to optimize performance, right? Someone might also say Slack eats up a lot of memory, and then you have to go optimize memory capacity. But for those kind of optimizations, you're usually optimizing only one thing at a time, right? And also, if you make your algorithms more efficient, your code more efficient, it's usually pretty portable, right? And here's the last thing I think that's going to surprise people is that the tools generally work. There may be times you get an error message in GCC and you're like, what does that mean? Put this into Google and still, what does that mean? That being said, they still work really well, right? Like, I've been programming for more than 20 years. Only about once in my career have I ever encountered a scenario where a compiler produced incorrect, code. It actually had a program that the C code is correct and the program behaved incorrectly because there's actually a mistake in the compiler, right? That's only happened like once in my 20 years for me. So the compilers are usually, giving out the right answer, but also highly automated, right? You tell TT3, -02, -03, and it runs off and does a pretty good job, right? And so it doesn't require kind of a whole lot of tuning, right? A lot of developers don't spend a lot of time thinking about the compiler flags because they aren't super important to them, right? It does a pretty good job out of the box. These things, all three of these things are perhaps different in hardware. And so that's why it's worth making folks aware of this, right? And so, when we're doing hardware design, simply just getting it working or just getting it implemented, that's the starting point, right? Actually making it work well in physical hardware as well as verifying are large hurdles, right? And the reason why is when you write code for, a processor, the compiler actually, compiling down to assembling that general machine code, it's pretty good at that. There's optimizations that are pretty good at that. When it comes to mapping your RTL to a physical implementation technology, there's some things that CAD tools can do extremely well. And occasionally, and sometimes unpredictably, they do a poor job, right? And so kind of looking over the shoulder of these tools and seeing what are they handling well, what are they having trouble with. And then unfortunately having to roll up your sleeves and go figure out, okay, here it actually had trouble, and how can I change my design or change the tools to make it do the right thing? That's going to be significant effort, right? So actually getting it to, even if you have correct RTL Verilog, to get that to be a efficient hardware design is a lot of effort, right? One of the classic sources of time is, when you're writing Verilog, you don't know where the delay is, right? You just kind of write hardware and you go with it. But when you start working on optimizing your design, perhaps you're targeting a very high clock rate. To get a very high clock frequency, you need to have a very short critical path. And like I said, when you're writing a Verilog, you may not know where that critical path is, right? But then as you start trying to optimize that critical path and make it, shorter and shorter, and you keep finding in various places, you need to keep adding in registers and moving logic around, and that can be a lot of effort, right? And that's just getting design optimized, right? Of course, you don't want to build a chip that's, permanent once it's manufactured that's incorrect. So you need to spend a lot of effort also verifying both the original design, the optimized design that's been physically implemented, all these things, right? So there's so much more effort to make the same amount of functionality. That's part of why, research, like I've had in my research group and some of my colleagues were trying really hard to improve the productivity of hardware design. It's kind of key phrase I keep saying is improve productivities, because it's, per feature, per unit of, delivery, it's so much more work than software, and we're trying to close that gap. But there's a very large gap right now. Additionally, as I said, optimizing, there's 3 metrics, right? We're talking about PPA. Usually you're worried about all 3. And the trade-offs are very technology dependent, right? You make one thing makes sense one year, and then, 5 years later, a couple process nodes later, all of a sudden a different spot in the design space, and another optimization makes sense. So this is going to change. And then I said this last one is the tools are really quite grouchy. Now, fortunately for you, we're not going to be using any of the back-end tool flows in this course. But if you did do that, you would quickly see that these tools are not the same as your software flows, right? They require a lot more human intervention to even just do things, right? So GCC, for example, when you run it, you kind of take it for granted. Oh yeah, it just runs. It's GCC, right? It's a compiler. But what's it doing, right? It's going in and reading your files, it's parsing them, checking for correctness, all that kind of stuff. Creates an AST, does a bunch of optimizations to the AST, a bunch of perhaps additional optimizations trying to figure out the target platform. Produces assembly, and then from the assembly, it actually assembles it into machine code, and then maybe does the linking to actually make that work out. So all these various steps. You don't think about that. It's kind of there's multiple tools inside GCC they're kind of all running back to back and kind of get taken care of it. It's not so easy in hardware, right? In hardware, usually what's called a tool flow, where it's multiple tools running, and oftentimes your design team has to write the automation and scripting that kind of passes the results from one tool to the next tool in that flow. And these tools require a lot of parameters, a lot of tweaking of the flags and options. Some people's entire job is just maintaining a tool flow, not even doing design work. It's a lot of work, right? That's just getting the tool flow up and running and doing that. But like I said, plenty of times you're going to find these tools need to be nudged or tweaked. They're producing not optimized results, not the way you want to be optimized, or worse yet, they also produce bugs. Like I said before, once in 20 years I've had a compiler bug have an actual producing correct assembly. For any significant hardware project, you will have a CAD tool produce incorrect hardware with almost near certainty at some point, right? And so there's a zillion tool verification processes done to try to verify the hardware produced by tools, make sure the tools themselves aren't breaking, right? Yeah, so there's just so much oversight required, right? So to summarize, right, it's just a lot more work, right? It's more work to optimize and verify. You're optimizing for multiple metrics, and the tools are harder to use and more grouchy. So yeah, it's going to be a journey, but we're going to try and talk this more agile approach to try and make these problems lessened, right? And it helps. The agile approach can help lessen all 3 of these kinds of issues. That's why we're kind of remind ourselves that talking about agile versus waterfall, right? And so the extremes we saw in the very first lecture, right? In waterfall, you try to do one stage completely before moving on to the next stage. So for example, you might say, first you design it very carefully, you specify each part of the design, then everyone goes and builds their specific pieces of the design, then they go off and integrate those, maybe you need to optimize and verify it. And kind of the idea of waterfall is you kind of do everything at one stage before moving on to the next stage. If you ever have a situation where someone needs to change something late, oh man, they're going to cause a lot of problems because we already finished that stage, right? If someone comes out in the optimization stage and says, hey, I want to change implementation in a significant way, we already did the integration, right? It's going to cause all sorts of headaches, right? And so the result is that the optimization and verification often end up being repeated, even though it's kind of advertised as, it's a single stage, move on to the next stage. No, because you optimize something, then you go verify it, and then you find a bug, you find another bug, and then you go re-optimize again. So even though this looks great on paper to a planner or a manager, you really do end up doing these stages multiple times, right? Which is why just embrace that from the beginning. Go agile, right? You're going to design it, implement it, optimize it, verify it, and then the key thing is you want to start doing all these things early, right? You want to start the verification early, you want to start the physical optimization early, you want to start all these things kind of early and kind of see how they're going, right? That way there's going to be less surprises at the end, right? If you have a hard design, you go through the entire process and you find out at the end that, it's 4 times more area than your budget. that's a big right? If you can recognize that early on, and you can perhaps realize, oh my gosh, I either need to drastically rethink my architecture, or I need to um, change my budget, right? It's good to know that early on, right? And so we've talked about this, right? Agile kind of incrementally add features, but the other key difference is, and this is one of the best features of Agile for hardware, is you can go around the loop multiple times, right? It's really hard in the beginning to know how certain things are going to be mapped by the tools, how efficiently they're going to turn on physical hardware, and getting that exactly right. Now, you might be able to get some qualitative, high level understanding. Oh, yeah, well, maybe this, last time this is the right choice versus this other choice. But it's hard to know that for sure, especially when you care about the exact, concepts and those trade-offs, right? And so with an Agile approach, you actually can see the numbers, right? And be like, oh, shoot, this architecture is getting a certain trending a certain way, and perhaps I should also try this other architecture and see that right away. And so, yeah, start overlapping these processes, start getting the physical design process started early, the verification process started early. So how we can kind of see what's going on. And we argue, people are excited about Agile design, that the more times you get around this loop, the better your design is, right? The more times you have to recognize a gap and to revise it and to do it again, and you keep making your design better and better and better, right? You only get one shot. It's hard to get that right the first time, right? So yeah, close that loop, go around it multiple times. Cool. I'm gonna pause for any questions. Okay, so this is a one-slide summary of a hardware design flow. So of course this is very, very superficial. I believe 222 A and B are great classes if it's interesting to learn more about this in the CSE department. But this gives you enough understanding to kind of be aware of some of the main things that go on, right? So, the goal of a hardware design tool flow is, given some sort of design, perhaps an RTL like Verilog, to produce a chip design. It can be handed off to the manufacturing group to actually, work with the mask machines and, actually make a chip. And so this is a cartoon view of the tool flow, perhaps from, let's say, 1975, right, or 1980, because they're way more complicated now. But this still gives you a sense of the main stages, right? So given your design, there's a step called synthesis, which takes your Verilog and turns it into things that map to your target technology, right? So for example, if you write a certain statement, in Verilog, and oh, well, here is, let's say an AND. Well, that needs to be mapped into an AND gate in your implementation technology, right? So working with a ASIC technology, you may have what's called standard cells, where it's a standard library of, these building blocks, things like AND gates, registers, etc. And so let's go ahead and map those. Okay, so, you wrote Verilog this way, and, well, I'm going to choose. Well, you know what? There may be 5 different types of AND gates. Which AND gate am I going to try? I'm going to go with this AND gate for now. And, maybe later on it'll change it. But so originally you have, this Verilog, which is this very abstract thing, and you turn it into something kind of concrete. Okay, I'm going to use these components, right? I'm going to use these components to exist. And so these are components that maybe they're resources on the FPGA or resources in your ASIC chip flow, but at that point they're just mapped to resources. But these resources are kind of just abstract concepts. Or they're not they're not, they don't exist, right? The next step is placing them, right? Okay, well, now I've chosen the resources I want. I need to figure out how to put them down in 2D, right? And as we're seeing very soon, hopefully, perhaps we'll be talking about how to place them in 3D, right? But for now, it's been 2D for, decades, and maybe 2D for the remainder of the decade, but 3D is, hopefully not too far off. So how can I go about placing these components in a way that makes sense, perhaps reduces the length of wires? Because that's the first step, is actually running the wires, right? That's the routing. So you may hear people say P&R, or placement and routing. That's kind of the point. Is you synthesize to find the blocks you're going to be putting down, the components you're putting down from your technology library. When you're choosing a certain ASIC library or a certain FPGA, you have components you're working with, right? So the synthesis process maps those components, and then you need to put them down physically, and then you need to connect the wires, right? And you can imagine the routing, you have to worry about crosses and how to, do various things and shorten wires. And eventually, you notice some more steps not shown, you get a chip design out. So these are 3 major steps, right? And the biggest difference between this kind of idealized picture and what happens in practice is that you end up running the tools a lot more times in a flow. You end up realizing, oh, wait, I synthesized originally and I placed and routed, but after placing and routing, I realized I have this horrible critical path. If I go back and actually use a different component here and then move this other thing here, I can make this routing shorter, right? And so a real tool flow is going to often have, run so many stages multiple times, or tweak it, or take the output of one and then go back and tweak it again. There's also a lot of steps in between about, perhaps correcting or adjusting for various manufacturing details, right? So when you're manufacturing advanced chips, there's all sorts of concerns about, oh, I need to do certain things for, things like electromagnetic interference or crosstalk between wires, or things about making it manufacturable in the first place, where there's certain limits to the lithography. That's the process used using light to make the chips that, you need to make sure that certain things are met. So there's a lot of other steps kind of squeezed in here. And then, of course, as you're doing this, you're probably going to want to verify it every step of the way to make sure one of these tools didn't break your design. Because they're trying their best to kind of optimize for various constraints or to map the technology in some way, but they can introduce errors. And so let's say, you had correct RTL, it was synthesized correctly, and then the media placer did a good job, but then the router, accidentally connected the wrong wire. Well, that's still going to lead to a bad chip, right? So you're going to want to check every step of the way, and you might say, oh, why not just check here at the very end before you manufacture it? Well, number one, this is really slow. This is a very detailed design. At this point, you trust almost nothing. So you're checking every single wire, every single transistor at that point. So it's very slow to check at that point. But also, if you see a mismatch, it's hard to know where it came from, right? So if you check kind of at every step of the way, you have a better odds of perhaps identifying, localizing where this bug came from. Like I said, more often than you'd expect, these bugs aren't just from your design, but they're actually from the tools, because these tools are being asked to do very challenging things, and they have kind of a very different usage flow. You think of something like a compiler like GCC, right? GCC as open source is kind of, really won out, or, LLVM Clang. It's open source because so many people will use them, and so many people will contribute to them, right? These are heavily used things, and so like, if there was a bug, someone else should have already come across it, and it should already be fixed, right? Your design's not that unique. It'll happen, right? There's millions, maybe perhaps hundreds of millions of users, right? It's just heavily pounded on tools. These hardware design tools have, orders of magnitude smaller of a user base, right? Even a large design team of thousands of employees may run some of these tools only, compared to a handful of number of times. And so you're talking about, instead of having millions, hundreds of millions of users in the world, maybe thousands, tens of thousands of users, if even. And so these tools just aren't, battle tested the same way that compilers are, right? It's part of why there's perhaps more bugs in them. And so, yeah, you really need to kind of verify and be very careful with these. Cool, I think that's the last for design. So I want to make sure I'm going to pause any more design questions. Like I said, so yeah, go ahead. Definitely, yeah. So the question from chat was, or spoken, I should say, was, given that these tools may have bugs, what can you do to be proactive about, designing differently or putting some sort of backdoor to help debug or prevent these bugs? It's an entire important field. There's kind of two key phrases you might hear is DFT and DFM. So what that stands for? DFM is design for manufacturing. So that is, what considerations do you put in your design process to make it easier to manufacture? Like I said, there's a lot of concerns in these modern chip technologies about how to make certain things map well to lithography and such, or just to get high yield, right? If your chip, when you make them, most of the time they don't work. Some of the time they do work. If you can improve your yield, that matters. So DFM is really important. DFT is the more important one, kind of answering your question, which is design for test, right? So definitely, I've been mostly talking about the RTL level of, okay, well, how do you make sure our design is easy to test at this level? But they actually design all sorts of ways, not just for test, but they also can think about, perhaps if I, design modules in a certain way, I can formally verify not just the RTL, but perhaps the RTL mapping the various stages, right? Proven equivalence check between what was produced by the tool after optimizations versus what came out there. Additionally, you're worried about bugs in the tool flow. There can also be manufacturing bugs or errors, right? Not every chip manufacturer is guaranteed to be perfect, right? And so an important part of the manufacturing process is after the chip is made to test that chip before actually putting it into a device, right? And so there's an additional testing process there. And to aid that testing process, there's often hardware inside of the chip that is only used for that moment. So, this very expensive manufacturing machine, which, is making chips and making an entire wafer. There's that moment when the tester, which is an actual hardware device, that clamps on and talks to one of these chips or dies. And it's, running diagnostics to see, was this chip properly manufactured, right? So to ease that process, there's actually hardware in these chips that's used only for that moment. And then once you decide that chip passes the test, and you take it out and put it in a device in the actual product, it's never actually used, right? That functionality is somehow disabled. And that's there, right? So yeah, so there's definitely stuff for this DFT. There's definitely stuff put in for testing. Yeah, so there's a whole set of stuff, right? Because at the end of the day, people's job is to make reliable products for the lowest cost. And yeah, if you can put a little extra hardware into your design for testing, they can reduce the amount of time you spend using that expensive testing machine. So thus you can get more chips out per hour. It's gonna be worth it, right? So yeah, people definitely do that. Great question. Well, cool. Okay, so that was kind of just, a bird's eye overview of design optimization and physical design. Just to kind of be aware of some of these major things. And we're kind of talking about specific optimizations in the coming lectures, right? So first, let's talk about memory. So why worry about memory? Well, if you have a design that actually uses memory, which is, most or almost all designs, memory is a really important cost contributor, right? So if you think about the entire price of a manufactured system, off-chip memory is actually a significant fraction of that price, right? If you've ever bought, a server, and you probably had a thing full of DRAM, you're aware of how much, memory costs, right? But even if you aren't buying a server, right, you're paying for memory more places than you might realize, right? It's not just the price of that memory chip. It's also the entire integration, right? You have to have, your custom chip and then the circuit board attaching to the memory and then all the wires in between. And all those wires are pins on your chip. And those pins can contribute to area. So as we said before, area is kind of your proxy for cost. And so you may have a situation in which that a non-trivial fraction of the area of your chip is actually just having the pins to talk to memory. And so depending on what memory you are talking to, or what kind of memory structure you have, you can change how many pins you have. And that's a huge knob you have to kind of control your cost, right? And then of course on chip, how much memory you have is directly related to area, right? Which is also directly related to cost, right? If your chip requires hundreds of megabytes of stuff on chip, that's a heck of a lot of area, right? That's gonna be a big chip. If you can get by a couple kilobytes, that's gonna be really tiny, right? So memory is something that can really impact your cost. And it's one of these things where if you can get your handle on it architecturally and figure out how to kind of reduce or optimize your memory usage under certain metrics, you can really impact your design's overall cost in very big ways. So if you remember your architecture courses, you may remember that memory is kind of this important limiting factor a lot of times, right? So maybe you remember memory latency is problematic. Talking about off-chip memory is, much, much, much higher latency than perhaps typical on-chip frequencies or clock rates. And so you have something called, perhaps the memory wall, right? We have this problem. If you go to memory, you have a long time waiting. So we have things like caches to try to overcome that, right? Other times, you have an application which is not so much about memory latency, because the architecture is able to handle latency. It's more about bandwidth, right? How much data can you move per second or whatever. And yeah, if you have limited bandwidth, that's a problem. So for some very intensive applications, you just need more bandwidth. You look at some of these, high-end GPUs used for gaming or, machine learning. Yes, they have a lot of compute capability on the chip, but sometimes they really are worried about having that, GDDR6, HBM2, HBM3, super high performance memory in order to get the bandwidth, right? So bandwidth also can matter. And so why is memory so inevitable? It's kind of the central component to a von Neumann architecture. And, a lot of these things are von Neumann-like, or even if they're an accelerator is perhaps not von Neumann, still need it, right? It holds your data, right? It holds your data for the input and output. It holds perhaps intermediate application data and state. Maybe your application can fit perfectly in, custom map registers that each serve their own purpose, but more often than not, you need to kind of overflow into memory of some sort, right? Whether it be on chip or off chip. And if you have time to think about this maybe sometime, you can kind of appreciate memory perhaps through a different lens, right? You kind of think of memory as so fundamental. Oh yeah, I have memory to store things and grab things. But in this course, you've also been designing custom circuits where I can give you a problem specification. You can write Chisel. Oh yeah, I want something that does A, B, and C. Well, I can just, wire this together, wire this to this, wire that to that, right? It's like very direct data flow. And what's interesting is memory is kind of just like, rather than just being a storage, you can almost think of it as like a super connector in a way, right? Where you have different entities operating on the same data eventually. And, if you're designing custom hardware, you can, I can select, entity A, producer, to entity B, consumer, no problem. But if the producer and consumer don't know who each other is at the time the producer is producing and the consumer needs it, you need somewhere to put that data, right? That's going to be memory, right? So memory is kind of a way to communicate through data in time, right? Where if you don't know which components are producing memory, as producing a data that's used as a important later on. You don't know who's talking to who. You don't know how to put those wires in. So memory, in some ways, think of it just rather than just like a storage. Think of it like a super network where it's like all-to-all connectivity, right? Where basically you kind of put things in these memory locations, almost like a mailbox, where I can kind of put it in there, and someone else later on can go check their mailbox to see if that data is there, right? And so this is true not just in hardware design; it's even true in CPU, right? How do you use CPU memory in software, right? You use memory to hold intermediate data as well as to communicate between different parts of your code. You may not necessarily know to be communicating to each other, right? And so, memory is pretty fundamental. It's pretty important, but it's going to be really important to cost. So if we can figure out a way to get a handle on it, we can really do ourselves some favors. So talk a little bit more about memory. I'm going to just do a kind of a brief reminder of some of the main terminology in memory to make sure we're on the same page. So we're talking about memory, of course. There's a certain capacity, right? Reason we're using memory to hold data, right? So how big is it? Some number of, words, bits, bytes, whatever the units are, but how much does it hold? There is a latency for an access, right? How long it takes to get data, or perhaps perform a write if you're storing. There's your bandwidth, which is the rate at which you can get data in or out. And so as I said in the last slide, right? Sometimes you care more about latency, sometimes you care more about bandwidth. And so kind of being aware of these two different distinctions, the rate versus the delay. When you hear someone say memory request, that's, a transaction being sent to memory. I want to read this location. I want to write this other location, right? And then, when talking about the memory, you might hear things like, like the access width, for how wide is the channel or something, right? Even though I'm trying to get, some amount of data, how much data am I getting per unit of time? Am I getting, a single bit? Am I getting bytes? Am I getting, hundreds of bits, etc. And then when you talk to memory, software, it's easy, right? You just kind of write things and it's a given, the compiler's gonna map those to load and store instructions. In hardware, in order to get to memory, you need to go through a port, right? There's some way these bits are arranged, and a port's the way you get in and out of memory. And so a port has a type, right? It can be a read-only port, it can be a write-only, or perhaps a read/write port. So, for example, if I have a memory that has only a single port, that means I only can perform or only initiate a single memory request per cycle at most, right? Perhaps maybe there's even limitations on that too. But if I want to do 2 memory transactions per cycle, I'm going to need 2 ports on that memory, right? And so number of ports is going to be a really important design constraint, because depending on implementation technology, you may have a very limited number of ports, right? Usually memories have at least 1 port, right? Because otherwise, why are you doing it? But some of our technologies don't lend themselves well to having more than 1 port. You get just 1 port. That's it. It's one read/write port. Other times, if you really want to get more ports, you can take a cost hit to have a 2 or 3 port memory, whatever. But there's going to be caveats to that. So number of ports is a really important constraint on memory. And this one's a little bit perhaps higher level than just inside the details of the physical circuits for memory, but sometimes there's a notion of how many requests you have in flight, right? So if memory takes a certain latency, but that memory request doesn't take up all the resources, a single memory through a single port may be able to do multiple requests at the same time, right? You send one request one cycle, that request then takes another cycle to come back. While you're waiting for it to come back, you can start another request, and that could also make progress, right? So you could have multiple requests in flight. And so when I say this term request in flight, I mean how many requests are in progress at the same time to the same memory. And of course, if you have more of those, perhaps you can get more bandwidth. So to relate those requests in flight, there's this tool called Little's Law, which I think is just really, really helpful. If you take an architecture course from me, you've already heard me rant a bunch about this, but I'll do it again because I think it's just so fundamental and helpful. And what it is basically says that, parallelism, i.e., in this case of memory, for example, number of things in flight, is simply throughput times latency. And you can, solve the algebra, change, which things on which side equal sign here. But if you ever wonder how do I kind of relate between these 3 things, well, this is the answer, right? So, for example, people often ask, oh, well, isn't throughput just 1 over the latency? That's only true if you only can have one outstanding thing at a time, right? If you can have parallelism, you can have multiple requests at a time, then that's not the case, right? And this equation helps tell you what the right answer is. And so that's kind of the point, is that understanding how these things relate, right? For example, the most common scenario is that you have something which latency you cannot improve, and you have a certain throughput goal you want to reach. Like I need to get this much, and that's the only solution is parallelism, right? And this matches real world intuition, right? Like let's say I'm doing something like making a sandwich, and well, it takes me some number of minutes to make a sandwich, so I can make only so many sandwiches per hour. And if I need, make enough sandwiches to feed a large group of people, and I only have 4 hours to do it, I determine, oh shoot, I'm not getting enough sandwiches done per hour to feed this large group of people, right? And so, the obvious answer is have someone else also make sandwiches, right? And you have more parallelism, and you get more sandwiches per hour, even though the latency making sandwiches is still kind of constant in that case, right? And so, this is always kind of the forefront of mind. A very high level trade-off is thinking about how can I trade these things off, right? If I can improve latency, it's going to reduce perhaps the need for parallelism, or perhaps maybe this gives me a higher throughput, depending on what your goals are. And so, being aware of these things relate is very important, right? Another thing to point out, people often worry about, oh well, my workload doesn't quite match Little's law because it's very bursty, right? I use a lot of bandwidth, and I don't use very much bandwidth or whatever. The nice part about Little's law is that it actually works for averages, right? So it's taking the average parallelism as the average throughput, the average latency. And so if you're in a scenario where your workload's bursty and you're looking at it through Little's law, you're looking at these like average throughputs, average latencies, and average parallelism. And sometimes those individual metrics might be a little misleading, but sometimes they're not, right? If you have a situation where your thing is really busy and it's, maxing out your parallelism, and other times it's largely idle, and you see a low average parallelism, the lesson is still right that your thing is mostly not using very much parallelism, right? That intuition is still correct, right? And so the averaging effect of the Little's law is actually really helpful in practice. I think it's a really, really good thing. This is, useful in far more than just hardware design. This is, a general systems kind of concept, right? Cool. I'll pause for any questions on that. Okay, so make sure we didn't skip a slide. Great. So when we're talking about memory, right? Our goal is to improve performance and reduce cost, right? So usually memory, if you're not careful, is going to be a performance limiter for you. So you want to make sure memory is not a performance limiter, and you also want to reduce the cost. It's kind of usually two things. It's kind of usually both. In both cases, you're trying to decrease something, right? And so what are the main points of pain typically in memory? Well, number one, latency is too high, right? If you're going off chip for memory, usually the delay to get the data and pull the data out and get it back, that's too long, right? Another common one in hardware design is you want too many ports, right? I want to have a 20-port memory. Your physical design teams can tell you, no way, right? And so how do you make that work, right? You might need to figure out ways to have multiple, users, in this case, users or hardware components, share a port to memory, right? Perhaps that'd be a great place for Windows arbiters we spend so much time talking about, right? You can have multiple entities that share a memory port and use an arbiter to choose who gets to actually talk to the memory port, because only one of them can use that memory port at a time, right? And then finally, is bandwidth issues, right? You have a workload that's pretty demanding, and the memory, you figure out a way to tolerate the latency, but the bandwidth just isn't there, right? So how do you deal with that, right? And so, like I said, this is one of those places where an architect can have tremendous impact and really save a lot on your overall system design. And it's worth doing this kind of first. Kind of how we talk about optimizing software, usually they say optimize the algorithms first. Here we are designing hardware, I say optimize your memory usage first. That's kind of my equivalent, advice, right? So really think about how you can kind of push on capacity, at least understand what it would take. Maybe I can do these things and reduce capacity to this extent. To reduce capacity further, I need to do some sort of, super obscure compression thing. Maybe you don't do that the first time, but you should at least be aware of it, right? And then after you reduce capacity, you also want to try and find the cheapest memory you can, right? So it's cheap, dense, right? More bits per square unit area. And so figure out, what is the cheapest and smallest memory you can get by with, right? Architecturally, like I said, try and figure out ways to tolerate that latency. That way you're not just idling the entire time waiting for memory. If you go through the entire effort of building a specialized hardware accelerator, and it turns out that most of the time it's just sitting there idle because it's waiting on memory latency, well, what was the point, right? And then finally, you can figure out a way to perhaps reuse your data better. You can also perhaps reduce your bandwidth demand, right? Which once again lets you use a cheaper memory and make people happy. And so there's a whole variety of memory technologies. We're not going to get into them in this lecture, but you may remember the memory hierarchy from your architecture course, where you talk about there's some things that are the things that are usually the fastest are usually the most expensive, and the things that usually are the slowest are usually the cheapest. It's kind of this general continuum of choices here. And same thing kind of for energy, right? Where things that, perhaps, actually energy is kind of more of a wash depending on what you're trying to do, right? Off-chip energy, of course, can be much bigger than on-chip energy, et cetera, et cetera. Cool. Okay, so let's try some optimizations. First one, let's talk about banking, right? So the problem is that somebody wants more bandwidth than I can actually provide, right? And, as I said before, sometimes your technology is kind of a limit. I can do one port easily, 2 ports. If you're willing to pay a premium, I can get you 2 ports. But if you want what it looks like articulately a 4 or 8 port memory, that's not going to happen at the circuit level, right? And so the solution to that is something called banking, which is basically if each individual memory can only provide so many ports, break up your memory into multiple banks that each provides those ports, and thus in aggregate across all of your banks, you have enough ports, right? And so, each bank can serve requests independently, and so that way you kind of can get this going. So, thinking about from a systems point of view, this is like sharding, right? You're kind of breaking it up. And this is one of those things where, having this as a knob from your generator could be really handy, right? You'll be able to say, you know what, maybe I'll put the capability of my design and have the memory be banked, but I don't know. Is it going to be 4 banks, 8 banks? What's going to be the right number? Parameterize it. Make that a generator feature, right? And that's the point. And the reason why this works, of course, is that each individual bank, can obey your technology limit for number of memory ports. And then, by having multiple banks, you can kind of add up the number of ports to get the aggregate number of ports you need. Now, this all sounds great in an idea, but let's talk about some of those actual caveats, right? So if you start breaking up memory into multiple banks, the question is, how do you break up the data, right? Well, you have 2 choices, right? You can partition it. This is kind of like that sharding example from, like I said, distributed systems, where you say, okay, well, if I have n banks, each bank gets 1/nth of the data, and that's going to make sure I send the request to the right bank, right? So hopefully I have, a uniform distribution of requests such that the requests uniformly fan out across my banks, and, that works out. Sometimes it's actually not going to be what you want. Sometimes maybe when you want a lot of banks, you're perhaps going to want maybe a lot of read-only ports and not very many write ports. In those cases, maybe you consider replicating your data. Of course, so when you replicate your data, now when you're banking, it actually takes more memory. But, you actually can get the number of read ports you need. And when you have replicas, of course, you need to make sure that they are consistent, right? Make sure that, updates go to all of them at the same time. But these are the details, right? But high level, you can kind of see out different ways to kind of bank it. And then when it comes to how these ports are worked, right? You can figure it out, right? Sometimes for banking, you can have independent ports or shared ports, right? You can either have expose all the ports for all the banks externally, or perhaps kind of have the appearance of the ports and then internally kind of map them, right? And then finally, sometimes banking is kind of inevitable, which is kind of surprising, right? Where sometimes in an application you have a demand for so much memory capacity. Because each individual unit of memory can only be made so big, you kind of end up with a lot of, pieces of memory because you just need that much capacity, right? So you kind of already have banking effectively, right? And so as a result, you actually end up with surplus bandwidth, where you actually have more banks than you need, more bandwidth you need, but you have all this memory because you need capacity. So it's kind of the same banking kind of optimization, just viewed from another angle, right? Cool. Questions on banking? Another one is smoothing out bandwidth demand. And this actually is a really general problem throughout all of engineering, not just even computers, where when you're designing something, there's this ratio that comes up of, what's the difference between the peak demand versus the average demand. And for me, a really great example of this is imagine like a freeway or a road, right? Where, perhaps it's a road well or a freeway well, and there's times when it's really crowded and there's times when it's really empty. And, when you're sitting in traffic, when it's really crowded, you're thinking, oh man, they should have, built a bigger freeway here. But then you also need to recognize that when you go zooming by there and it's no traffic, it's largely underutilized, right? And chances are, even for some of the most busy freeways, if you were to average the car traffic over them over the 24-hour time period of a day, you'd probably find that the average traffic is actually pretty modest, right? And so kind of the result is, how much of a premium are you willing to pay to make the bursty peak scenario okay, right? And that's kind of the question, right? Are you willing to, put in a 6-lane freeway just to try and reduce the rush hour traffic, even though on average your freeway only needs 1.5 lanes, right? If you average over 24 hours per day. And so the same thing happens in hardware where, what kind of, capability to put in there for your memory bandwidth or something like that, where peak versus average, right? And so anything I can do to smooth it out and kind of reduce the gap between the peak and the average, that makes my job a lot easier, right? Because sometimes in order to, guarantee the implications I want, I need to, handle the peak. And so I'm kind of forced to size things to the peak, but really the actual average demand is the average. So if I can somehow, as an architect, smooth out my demand, so same amount of bytes are transferred just over a longer time period, make the peak and average the same, I can get by with a lot less bandwidth, right? And that makes my job a lot better. I can get by with cheaper memory, less bandwidth, that'd be so much better. And so to smooth out memory bandwidth demand, there's two common approaches, pipelining and double buffering. So let's go ahead and talk about those. For pipelining, one easy way to do it is something what I call overlapping communication and computation, right? And you can imagine that, you're a piece of hardware, while it's reading and writing large blocks of memory, it's kind of loading or unloading its state, and then it starts computing, and then great, okay, now I'm not, unload the output and then load a new input, right? And so as a result, you're either, communicating or computing at the same, but not both at the same time. If you can overlap these two, you can, of course, reduce your average bandwidth demand, reduce your peak bandwidth demand. Because right here you are, having this idle period, right? So peak idle, so that's going to have a lower average, right? If you can just push it all together, you can improve things. In this case, you don't just maybe reduce your average bandwidth demand, you actually may also improve overall performance, right? You're squeezing out idle time by taking advantage of parallelism, right? You have the ability to, do computation and communication at the same time. So in order to be able to do computation and communication at the same time, you need to have enough parallelism in your application such that, that you can be loading data you're not working on, right? Or vice versa. So if you have that ability to kind of load data you're not working on, what's one way to do that? Double buffering, right? So double buffering is the idea of, you've seen something similar for frame buffers, for graphics, whatever. The idea is, okay, well, if I have some amount of computing to do, some amount of communication tuned from memory, if I kind of treat my memory as two halves, and you can kind of, change halves to be, n in some ways, basically I can, load into one memory while computing on the other, and then the next phase I can compute the other one, right? So you can imagine, so I'm kind of, loading memory while I'm computing on it, and then I compute the portion I just loaded, and then load the other portion, right? And so if you're going to overlap computation and communication, you kind of need to have this ability to kind of be simultaneously loading and unloading at the same time. Double buffering is just one way to do this. There are other ways to do it, right? But you kind of see the high level. These are kind of high-level architectural tricks to kind of optimize your memory usage and memory patterns. Cool. Okay. So any questions on these optimizations? Okay, so when it comes to instantiating memories in practice, like I said, usually there's a lot of design intent and careful to work here. You don't just kind of, hand out the tools and see, oh, what tools, give me what you're going to give me, right? Oh, what memory am I going to get? No, you're gonna plan this out, right? So for off-chip memory, it's going to be a major design decision about what type of memory you're working with and how many channels, right? I'm going to be going with, LPDDR5 single channel, or I'm going to go LPDDR6 with 2 channels, or I'm going to go HBM or something. Like the memory technology and the interface and the number of channels, that's something you're going to be a very big first order design constraint when you're designing your thing. And, people looking at the cost, they're going to be very happy when you figure out to use a cheaper memory technology or fewer memory channels, right? So off-chip memory, you're going to have a very deliberate choice in that. When it comes to on-chip memory, for ASICs, right, your kind of choices are just SRAMs or registers. Registers, the tools do a good job of inferring, and you can kind of perhaps sometimes you want to nudge it because for a given technology, maybe actually a variety of registers to choose from will have different, area, power, or performance trade-offs, and perhaps the tools can choose those correctly. Sometimes better. When it comes to SRAMs, there's a whole world about how to pick the right SRAMs, right? And so for a given technology, to make an SRAM array is actually a really big specialized thing. It's not as simple as just a couple logic gates tossed down. It's usually something called a memory compiler, which makes a memory for a given technology. And so that's one option, is use a memory compiler. Given the foundry, you can go ahead and make your own memories. Other times, the foundry, i.e. the manufacturer, is going to say, if you're using our technology, here are some preset memories we've already compiled. Consider using these, right? And so when you get one of these memory cells or one of these memory arrays, it's going to be, okay, here's a 128-bit by 128-bit SRAM array. And that's not necessarily in the range of kilobytes or megabytes you need for your entire design. So you need to go ahead and take these and put these together to build up your memories the way you want them. And so sometimes you need to be pretty deliberate on instantiating these. When you really start optimizing, you need to kind of think about, okay, which memories am I using? How am I kind of stitching things together? And okay, when I chose to break up this very large memory into, let's say, SRAM arrays that are 128 bits wide, maybe if I actually go 256 bits wide, I have just certain trade-offs, and this changes, right? So there's some very deliberate choices here. So for ASIC, you're definitely spending a lot of time on this. For FPGA, fortunately, it's a little simpler, right? There's, of course, registers in FPGA. There's something called LUTRAM, BRAM, and sometimes URAM on Xilinx, right? But in other words, you kind of basically have your normal flip-flop registers, there's some sort of block RAM or BRAM, and then there may or may not be other exotic things that are vendor-specific, right? But the real goal here is actually get the tools to infer use for memory. So you write your Verilog in a way that the tools recognize, oh, wait, I should use my primitive for memory on this device and use that. And this is actually something you can do, right? So this actually does work, where for an ASIC design, usually the tools will not correctly recognize an ASIC memory for you. But for FPGAs, if you write your Verilog in the right way, they actually will optimize it correctly. And like I said, sometimes between LUTRAM versus BRAM, there may be a area performance trade-off that the tools can make a lot better than you can. So best is to have the tools infer it, right? So make sure you Verilog in a way where the tools recognize they can legally perform the specifications you requested via memory. The most common problem is you use Verilog in a way that prohibits this. And of course, you're thinking, wait, Verilog? I'm not doing Verilog, I'm doing Chisel, right? Yeah, so Chisel, if it's used correctly, you can get this right, but you actually can use Chisel to cause this inference to break. So sometimes you need to give what's called an intrinsic, to kind of tell the tools, I definitely want this kind of memory here. Hopefully you can avoid that. And so like I said, so for Chisel, normally you're just describing a behavior, right? And honestly, FPGAs, if you do things right, it's going to do the right thing. It's going to do the registers and the BRAMs for you, and you don't have to worry about too much. But for SRAM, yeah, you're going to need to be careful. So you want to, SRAM of course implies you're doing an ASIC. You're going to want to do what's called black box, where you have something that, meets the parameter specifications of that SRAM. And then you're actually going to put the, SRAM connections in there. And maybe use your Chisel very cleverly to make sure, you're limiting the number of ports you have and perhaps specifying your read and write ports. So Chisel, we can access memories, want access memories. You also can say, hey, I want to have a port, and be very careful and deliberate about it. So here's kind of the real world kind of caveats to all this memory stuff we've been talking about. But long story short is, from today, you've heard me talk a lot about how much memory is a very important design constraint. And architecturally, of course, it makes sense to, think about memory and how to use it. But there's also these kind of physical concerns we've been talking about today. So then wrapping up today, like I said, if you're going to do physical design optimization, you need to know why you're building hardware. You can't just program an embedded CPU to do what you need to do, right? So you have a certain performance efficiency goal. That's why you're doing this. Understand what that goal is and understand why the CPU can't reach it. And if you go ahead and start optimizing your hardware, make sure you measure your PPA and start comparing to the goal, right? If you just say, I want really fast, what does that mean, right? Use an agile process, close that loop early, find design issues early, and also find issues with backend tools, right? You don't want to write a whole bunch of designs and find out later on that this particular tool in your backend tool flow doesn't like the way you write Verilog, and it just barfs around it, right? You don't want to find out late, right? Get the tools running early, close the loop early. Of course, get my usual Little's Law pitch. You'd be surprised how many architects don't always remember this and are surprised by some of the very easy takeaways from Little's Law. It's a really helpful way to kind of view these things, especially how to kind of trade off latency, throughput, and parallelism. It's a very easy way to kind of understand their relation. And then the remainder of the lecture was, of course, optimizing memory. We talked about that's the first thing you should do in a hardware design, is thinking about what memory do I need and how am I going to perhaps reduce it or optimize it. And yeah, we talked about you want to get that figured out early, right? Because if all of a sudden in your design process you realize, we need to change this memory interface, that's going to cause a lot of complexity for a lot of people, right? So getting this figured out early in the design process, or at least having ideas on that early in the process, is make your life a lot better. And optimizations, right? We talked about banking, traffic shaping, trying to smooth out those peaks, right? Perhaps by doing computation communication overlap, double buffering, etc. So any last questions? Okay, that's all, folks. Have a good day.